Hey everyone, ready for another deep dive? Today we're going to tackle something pretty mind-bending, the dual nature of light and matter.
Yeah, it's definitely one of those things in physics that can really make your head spin.
You know, at first it sounds kind of intimidating, but I promise you it's fascinating stuff and totally worth exploring.
Once you start to wrap your head around it, it really changes how you see the world.
So we've got this chapter from a physics textbook that's going to be our guide today, and we're going to try to uncover how something as familiar as light.
Something we see every single day.
Exactly. How can it act like both a wave and a particle? And get this, that same duality applies to matter itself.
It's true. The stuff that makes up you and me and everything we see around us.
Okay, so to really get into this, we need to go back in time a bit.
Back to the late 1800s.
Yeah, picture yourself in a physics lab back then. Scientists are totally baffled by these mysterious rays they're calling cathode rays.
Imagine like a beam shooting out from a negatively charged electrode in a vacuum tube.
They had no idea what they were made of or where they came from.
It's a complete mystery.
And then along comes J.J. Thomson, a British physicist who decides to figure this whole thing out.
A real pioneer.
He sets up these ingenious experiments using magnetic and electric fields to try to manipulate these cathode rays.
He was basically trying to see how they would react to these forces.
And what he discovers is absolutely groundbreaking. He finds that these rays are actually streams of tiny negatively charged particles.
Which later became known as electrons.
Exactly. And what's even more amazing is that no matter what material they used for the electrode,
They tried all sorts of different metals.
these electrons were always the same. This was a huge clue that they weren't just some weird quirk of certain substances, but something much more fundamental.
A fundamental building block of all matter.
Boom! It's a major aha moment, right?
Yeah.
Suddenly, this simple experiment with these mysterious cathode rays unlocks a fundamental truth about the universe.
And it paved the way for so much of modern physics.
Now we know that these tiny electrons are buzzing around in every atom that makes up you and me and everything we see.
It's kind of mind-blowing when you think about it.
And think about this. All of our modern technology, from smartphones to computers to all kinds of electronics, it all goes back to understanding these tiny little particles.
It really shows how a single discovery can revolutionize the world.
Okay, so we've established that electrons are key players in the world of matter. But how do we actually get these electrons to break free from the atoms they're bound to?
Especially in metals.
Right. It's like they're trapped in a tiny metal prison.
Well, they're bound within metals, but scientists have figured out a few ways to coax them out. There are three main methods: thermionic emission, field emission, and photoelectric emission.
Okay, let's break those down a bit. Thermionic emission uses heat to give the electrons enough energy to escape.
It's like giving them a thermal boost to jump the fence.
I like that analogy. And then there's field emission, which uses a strong electric field to pull them away.
Imagine using a powerful magnet to yank those electrons right out.
That's a great way to visualize it. And finally, there's the photoelectric effect.
Now, this is where things get really interesting.
So with the photoelectric effect, you're shining light onto a metal surface, and that causes electrons to be emitted.
Not just any light, though. The light has to be a specific frequency.
Oh, wow. So you're saying that light can actually knock electrons loose? That's pretty wild.
It is. And it was this discovery that really started to reveal the dual nature of light.
Okay, I'm definitely intrigued. Let's dive deeper into this photoelectric effect. But first, we need to talk about this concept of the work function.
Yeah, it's an important piece of the puzzle.
Imagine it like this. Each metal has its own stickiness when it comes to electrons. Some metals hold onto their electrons really tightly, while others let them go more easily. This stickiness is what we call the work function.
It's the minimum energy that an electron needs to break free from the surface of a metal.
So it's kind of like an energy barrier.
Precisely. And different metals have different work functions.
So even in the world of metals, there's a whole spectrum of how hard it is for electrons to escape.
That's a great way to put it.
All right, so now that we understand what the work function is all about, let's shine a light on this fascinating photoelectric effect. What were scientists observing that led to this revolutionary understanding of light?
Well, they set up these experiments using something called a photosensitive plate.
So kind of like a very early version of a solar panel.
Exactly. They started shining light on it, and what they saw was pretty mind-blowing.
Okay, let's walk through their observations step by step, because this is where we start to uncover the mystery.
Sounds good.
First, they noticed that the photocurrent, which is basically a measure of how many electrons are flowing, increased as they increased the intensity of the light.
More light, more electron flow. Pretty straightforward, right?
It seems intuitive.
Yeah, at first it does.
But then things took a turn. They found that the stopping potential, and imagine this like applying a voltage brake to stop those emitted electrons, depended on the frequency of the light, not its intensity.
That's right. The stopping potential tells us how much braking power we need, and that relates directly to the energy of those electrons.
Wait, so even if you crank up the intensity and make the light super bright, you still might not be able to stop the electrons completely if the frequency of the light is high enough.
Exactly. And that's where classical wave theory really breaks down. It couldn't explain that observation.
Okay, and there's one more key observation that really threw things for a loop. They found a specific threshold frequency of light below which no electrons were emitted no matter how intense the light was.
It was like the metal was saying, nope, not letting go unless you hit me with light of at least this frequency.
Yeah. So I've got these three observations: the increase in photocurrent with light intensity, the frequency-dependent stalking potential, and the existence of a threshold frequency. And together, they created a major scientific puzzle.
A puzzle that classical physics just couldn't solve.
It was like the universe was dropping a giant hint that something was up with our understanding of light.
It was a sign that a scientific revolution was brewing.
And that revolution was led by none other than Albert Einstein. But that's a story for part 2 of our deep dive.
We'll pick up there next time and delve into Einstein's revolutionary explanation of the photoelectric effect.
Get ready for some serious insights into the quantum world. See you then. Welcome back to our deep dive. Last time we left off with a pretty big cliffhanger.
Yeah, that photoelectric effect really threw a wrench into classical physics.
It just didn't make sense with what we thought we knew about light as a wave.
Those experimental observations were totally baffling.
So how did scientists explain this? How did they solve the puzzle?
Well, that's where Einstein comes in with this truly groundbreaking idea.
I knew he'd show up somewhere in this story.
In 1905, he proposed this radical concept that light wasn't just a wave.
It had another side to it.
Exactly. He said that light also existed as these tiny packets of energy.
Like little bundles of light.
Yeah, he called them quanta, which we now call photons.
Photons. Okay, so light has this secret identity as a particle.
It's like it can switch back and forth between being a wave and a particle depending on the situation.
But how did this whole photon idea explain those weird observations about the photoelectric effect?
Well, Einstein's idea was that a single photon interacts with a single electron in the metal.
Okay, so one photon hits one electron.
Right. When the photon hits, it transfers all of its energy to that electron.
So it's kind of like a tiny game of billiards at the atomic level.
Yeah, I like that. And if the photon's energy is greater than the metal's work function,
The stickiness of the metal that we talked about?
exactly, then the electron has enough energy to break free and escape.
Like it's finally strong enough to jump over the fence.
And any leftover energy becomes the electron's kinetic energy.
The energy of motion.
Right.
I'm starting to see how this works now. So it's not about the total amount of light or the intensity. It's about the energy of each individual photon.
That's the key.
And that energy determines whether or not an electron gets knocked loose.
And since a photon's energy is directly related to its frequency.
That explains why the stopping potential depended on the frequency and not the intensity.
Exactly. Higher frequency light means higher energy photons, which give the electrons a bigger kick.
So you need a higher stopping potential to put on the brakes.
It all starts to connect.
What about that threshold frequency? The one where no electrons were emitted no matter how intense the light?
Right. That was another thing that classical physics couldn't explain.
So how did Einstein's photon theory explain that?
Well, according to his theory, a photon needs enough energy to overcome that work function barrier.
To break free from the metal's grip.
If the photon's frequency is too low, its energy just isn't enough to dislodge the electron, no matter how many photons you throw at it.
It's like trying to break a brick wall with a tennis ball. You need a lot more force.
Exactly. You need something with more energy.
So Einstein's theory with these packets of light energy called photons actually explains all the weird stuff that was happening with the photoelectric effect.
It was a really elegant solution.
Didn't he come up with an equation to explain all of this too?
He did. The equation is Kmax, HN S0.
I remember seeing that in my physics textbook.
It looks a bit complicated at first.
Yeah, but once you break it down, it's actually pretty straightforward.
It tells us that the maximum kinetic energy of an emitted electron
Cmax.
is equal to the energy of the photon, which is Hn.
where h is Planck's constant and n is the frequency.
Right, minus the work function of the metal F.
So it's basically saying that the energy of the emitted electron comes from the photon's energy minus the energy it took to escape the metal.
That's a really neat way to summarize the whole process.
Einstein's explanation of the photoelectric effect with these photons was a total game changer.
It revolutionized how we think about light.
But the story doesn't end there, does it? We've been talking about how light can act like a particle, but could matter actually behave like a wave?
Now, that is a truly mind-blowing idea.
All right, so we're back and ready to finish our deep dive into the dual nature of light and matter.
And last time we left off with this crazy question.
Yeah, if light can act like a particle, could matter also behave like a wave?
It almost seems impossible, right?
It does. Our everyday experience tells us that matter is made of, well, solid stuff.
Particles. Tiny little bits of matter.
And waves are something totally different. They're spread out, not confined to one spot.
So how could something be both a particle and a wave?
It's a real head-scratcher.
But as we've seen already, the quantum world doesn't always play by the rules.
Right. So in the 1920s, a French physicist named Louis de Broglie decided to tackle this question head-on.
He was a pretty bold thinker.
Yeah, he looked at the symmetry of nature and thought, well, if light, which we usually think of as a wave, can show us its particle side, then maybe matter, which we think of as particles, also has a wave side.
It makes sense in a weird sort of way.
I know. So de Broglie came up with this mathematical way to express this idea. It's called the de Broglie relation.
It's a pretty simple equation, actually. De Beach HP.
But the implications are huge. It's saying that every particle has a wavelength.
That's right. Even you and me.
So what does that mean? Let's break it down.
All right, so the equation says that the wavelength of a particle is equal to Planck's constant h divided by the particle's momentum.
Okay, so if a particle is moving really fast, its wavelength is shorter.
Right, and if it's heavier, its wavelength is also shorter.
And if you plug in the numbers for everyday objects like a baseball or a car,
Or even a person.
their de Broglie wavelengths are incredibly tiny.
We're talking smaller than an atom,
So small that we can't even detect them.
which is why we don't see baseballs diffracting through doorways like waves on the ocean.
We definitely notice that.
Yeah, our everyday experience doesn't really give us any hints that matter might be behaving like a wave.
But what about the microscopic world, the world of atoms and electrons?
Well, that's where de Broglie's hypothesis really shines. For tiny particles like electrons, their de Broglie wavelengths can be big enough to actually observe.
So we can actually see matter acting like a wave.
Well, not with our eyes, but we can see the effects. A few years after de Broglie proposed his idea, scientists were able to observe electron diffraction patterns.
Just like you get with light waves.
Exactly. That was the proof that de Broglie was right.
This wave-particle duality wasn't just some quirk of light. It was a fundamental principle of the universe.
It applies to everything, both light and matter.
So we're all just waves walking around then.
Well, not exactly. A little more complicated than that.
Okay, come on, then explain it to me.
The wave-like nature of matter is definitely real, but it's most obvious at the microscopic scale. In our big world where things are much larger, these wave-like aspects kind of average out.
So that's why things appear solid and have a defined position.
Right, but deep down at the most fundamental level, everything has this fuzzy, wave-like quality.
It's like the universe is hiding its true nature from us.
Or maybe it's showing us that reality is far more complex and strange than we ever imagined.
So we're left with this amazing mystery. The universe at its core plays by rules that are totally different from what we see in our everyday lives.
And the more we learn about these rules, the more we realize how much we don't know.
And that's what makes science so exciting. There's always more to discover and explore.
Exactly.
Well, thanks for joining us on this deep dive into the dual nature of light and matter.
It's been a wild ride.
It really has. We hope you learned something new and maybe had your mind blown a little bit along the way.
And who knows what other mysteries the quantum world holds.
There's a whole universe out there waiting to be explored. Keep those minds curious, and we'll catch you next time on The Deep Dive.